This is the thing that I sent you all via email over the weekend. Please note, this is exactly word for word from the front cover of the exam. So I would love for you to all make a formula sheet for this exam. You will need to turn it in to me with the exam. Formulas, definitions, rules on one side, one standard 8.5 by 11 sheet of paper, handwritten, your writing. No worked out examples. You get to turn it in. I will give you the normal table, the binomial probability tables, already printed and copied directly out of the back of the textbook, Appendix A and Appendix C. You'll get those for the exam. If you know how to do the calculations using the distributions on your calculator, you are welcome to do them that way instead. It's your call. You just have to write down what you did on the calculator so I know what you did. You have homework for me. Send it that way. Additionally, I thought this might or might not be helpful. That's the exam. That's the breakdown of what's on the exam. It's almost exactly equal points per section. Thank you. Very important. That way you know what's on the exam, roughly how much of each thing from each. Three questions from each chapter, roughly the same number of points in each section, roughly. And then it's converted to a percentage just like the first exam. Meanwhile, we were dealing with central limit theorem. And when I was talking about this, I said we got a sample mean. We got X bar. So I pull out X bar and I say to myself, I don't know how accurate that is. But given my idea of confidence with a normal distribution, I can then say, oh, let's look at z-scores and relate percentage information I know to z-scores. If I do that, the end of class on Friday, I said the middle 95%, is a table in our textbook, goes with a z-score of 1.96. There are several other z-scores of use on this table, which I have to re-find in our textbook. I ate it. In the middle of page 240 something, I swear to you, I didn't make this table up. Is that it, page 245? Yes, there it is, our middle table. So I see the middle 95% goes with 1.96. The middle 90% goes with 1.65. The middle 99% goes with 2.576. So let's think back to the GMAT scores that I was using it as example in this section. So those come from that table on page 245. What was the average for our GMAT data from Friday? Very first thing we put up on Friday, at the population average and standard deviation. Standard deviation and mean for our GMAT data was 520.78. Okay. Now remember, I took samples. How big were the samples I was taking out of this group? Wait a second, 86.0. I thought it was 80. Thank you. How big were the samples I was taking out of this group? Five. So if I'm taking a sample of size 5, I compute the standard error for a sample of size 5. How do I get the standard error for the mean? This was a formula we had on Friday. Oh, it wasn't SX bar, it was sigma. Sigma X bar. That is exactly what it is. It is sigma over the square root of n. So for me, with a standard deviation of 86.8 and a sample size of 5, my standard error is Out come the calculators. Say that again. 38.818. Bunch more decimals. I'm perfectly happy rounding this to 38.2, or even just 82, or just 38.8. Depends on what we're going to do with it. So here's my claim. I take a sample. I get a mean for that sample. How do I know how close that is? How confident am I that I'm close to that number 520.78 with my answer? Well, I can create an interval based on the size of my sample. That interval is going to give me the range of my sample mean. And the way I compute this range is to use the z-value of sureness I want. I only want to be 90% sure. Then I'll say, oh, a 90% interval comes from taking my average and subtracting z times the standard error, or taking the average and adding z times the standard error. And my choice of z depends on my choice of percentage. You want 90%, 95%, and 99%? I'm going to do at least two of them, so start with one. 90%? Okay, so if I'm doing 90%, the z I'm using is 1.645. The average is 520.78. I subtract 1.645 times the standard error I came up with, 38.818. Somebody give me a number. Say again. 456.92. Now do the same calculation, only this time instead of subtracting, add. What's this number? You take a group of 5 people, you average their GMAT score. 90% of the time, The number you get out should be between these two. That's a range for your sample average. But only a 90% range. So 90% of the numbers you encounter should be between these two. What if I said I wanted 95% of the numbers? I wanted boundaries for 95%. Well, 90% fit between these two. If I want to get more numbers, I'm going to need to make this interval bigger or smaller. %90 fit in here. I want to get more numbers. Do I make it bigger? Do I make it smaller? I need to make it bigger. And that's why the 95% z-value is, that's the one we wrote down on Friday. It was on the screen earlier. What's the 95% z? Which means we're going to multiply the 38.8 by 1.96. We're going to get a number a little smaller. We're going to get a number a little bigger. And if I wanted 99%, it would be even bigger, because the 99% number is 2.576. So I can get different range intervals depending on my confidence or my willingness to accept that some of the numbers will not be in here. So if I do a 95% range, my 95% range is going to be bigger. So I end up with a number that's smaller than 456 and a number that's bigger than 584. Questions? So let's change problem settings. Problem 8.3, here at the top of page 281, talks about bushings. The diameter of bushings turned out by a manufacturing process is normally distributed with a given mean and a given standard deviation. Problem 8.3. The mean is 4.035 millimeters, and the standard deviation is 0.005 millimeters. We can measure really accurately on our bushings. Every hour, we take a sample of 25 bushings and we measure them. Find out what their diameter is. So we're doing a lot of quality control on this particular manufacturing process. Yes, sir. Page 281. I turn around and I ask you, go through the questions here. What can you tell me about 95% of the numbers you see for the diameters you get? Now, what's important here is what I've said about what I am measuring. I am measuring the diameter of the bearings. So now I want to know what's the 95% range for those numbers. That range isn't asking about the average, it's asking about the individual measurements. So when I go to find that 95% range, I'm going to use the standard deviation itself. Where did the 1.96 come from? Say again? That's the z-score that goes with 95%. But notice this is this number. So I take 4.035 and I subtract 1.96 times 0.005. And here I take 4.035 and I add 1.96 times 0.005. What's my low number? Say again? No, what do I get when I finish this calculation? I want much more decimal places. I've got 3 decimal places after here, 3 after here. Give me at least 3 after the decimal. Maybe you can go to a 4th one.
For the top line, it's 4.0330. It's 4.036.
I don't get either of those numbers for these calculations. At least that's not what I have written down in front of me here. (4.035) minus 1.96 times 0.005. Aha! That's why I was very specific about the fact that we are not looking at averages yet. That's why I'm doing the standard deviation 005, not 001. Yes. (4.0252), and then the upper one is it's got to be bigger than this one. Now, Anna, you did 0.001, right? But that's the standard error for the mean. So if I change this question, and instead of saying, what's a 95% interval for the diameter, if I said, what is a 95% interval for the sample mean, that's where I change the standard deviation. That's, instead of doing sigma, I do mu minus 1.96 sigma x bar. Or if you'd rather, 1.96 sigma divided by the square root of n, because that's how we get that standard error. And then square root of 25 is 5. 0.005 divided by 5 is 0.001. So the low number in this case is 4.033. I mean, if I take it out more decimal places, I get 04. And you can go as many decimal places. I would go at least one more than the number we were given in any calculation we do like this. And then the top end, (1.96) times 0.005 over 5. This time, 4.03696. So there's a much larger variation range in the actual measurements. But when I average them, that range gets a lot smaller. If I saw a measurement of 4.0, I turn around and I take out 25 bushings, I average their diameters, and I get 4.020. What should I do? Take my sample, all 25 bushings. I average their diameters. I get 4.020. Everything's fine. Or, what do I do? This is where having a number is useless information unless we can make a decision off of that number. So if I see an average measurement of 4.02, and I say to myself, wait a minute, 95% of the time, it should be between 4.033 and 4.037, something's effed up. And I don't mean a little effed up, I mean really effed up. That's way too small of an average. Stop. Either my bushings are being made at the wrong size, or this number, 4.035, is wrong. But this is an indicator to me. That is way too far outside this region for me to be confident that I got something right. This is a problem. Now, I don't know what kind of a problem it is, whether it's a problem that one of my machines is badly calibrated, my batch of bushings has a defective material, maybe one of my stampers is stamping things in the wrong size. I don't know. But my first reaction is, hold on a minute, something's messed up. It could be that you fed me the wrong information, and 4.035 is not the correct average. Or it could be there's a problem with my manufacturing process. Stop making these. We're going to have to throw these out and lose money. A very long time ago, I had a summer internship at the physics department, University of Pittsburgh, working for Dr. Bill Cleland, and Bill was brilliant. Bill was working on a project called Atlas. Atlas was going to be part of the CERN super collider looking for the Higgs boson. This is that God particle that everybody was really interested in about 20 years ago, right about the time you all were born. And I'm looking at this project, and my job is to make amplifiers. That's all I'm doing. I'm building amplifier chips. And he says to me, here's your job for the next 3 weeks. You take the chips, you put them in the rig, you pull the lever, and you push the button. You pass it. If it passes, put it in this box. If it fails, put it in that box. This is going to be a boring job for the next 3 weeks. Within the first hour, every single chip I tested failed. So I went back to Bill and I said, this is not right. Something's wrong here. And it turned out the chips were fine. The error was in the number he'd given me. And we'd written the code for the chips wrong. So I said, oh, well, then we need to go in and change this. And we spent about the next hour rewriting the code for the computer program, and every one of those passed. I want you to understand, I was later told that each individual amplifier costs $125,000. And in an hour, I had tested well over 20 of them. That's $4 million worth of computer hardware that would have been thrown away if I hadn't said, hey, wait, something's wrong here. Let's go back and check what's wrong. Or is it an error in the number? And I literally only knew how to do that because of this idea. So I'd love to tell you this is worthless, but I saved $4 million doing this, personally. I didn't see a dime of it, but damn. The Atlas experiment, by the way, was a success. If you Google CERN Atlas, C-E-R-N, Atlas program, you'll find out what they did. It was very interesting. The same thing, I would make the same call if my number was way too high. The textbook says, what if you found 4.055? Well, again, 4.055 is way too big. I don't think it should be bigger than 4.037. And so my average being too big is just as bad as my average being too small. It's just not right. Questions? When I estimate an overall parameter with one of my estimators, like estimating mu from x bar is a point estimator. It's one number, a single piece of data. But ranges, like my expected range for the sample mean, are a little more useful. But in order for me to figure out that interval, I needed to start from a known population average. That's a problem. Because unless I measure every single one of my bushings, unless I test unless I get every single one of the GMAT scores that came through, I don't have the population information. I only have my sample information. So what I can do is I can work the other way around. I can create what's called a confidence interval for mu from x bar. So I take the point estimate I came up with, and I add or subtract a margin of error. Now, confidence is a percentage. So I'm going to say, how confident do you want to be that the population average is in your interval? Most of the time, I'm going to use those numbers. Occasionally, I might use something a little lower. I'm going to call the number alpha 1 minus the confidence level, expressed as a decimal. So alpha is 1 minus this number. Okay, wait a second. For each of these, I get an alpha. If my confidence level is 90%, what's alpha? But I want it as a decimal. Because I turn the 90% into 0.9, and I get 0.1. Similarly here, I get 0.05. Here, I get 0.01. Now, here's the sneaky part. For each of these, I want you to turn to table Z1, sorry, C1, the Z table. I want you to go to the Z table. If I want to be sure that the middle 90% is what I want, then in the normal distribution, I should have 10% on the outside, right? If I want the middle 90, then the outside should be 10. The outside is 10. That means half of that is up here, and half of that is down here. So I take my alpha and I divide it by 2. Now do me a favor. In table Z1, sorry, said it again, C1, not Z. It's a Z table. That's why I keep doing that. In this table, find me the Z value that goes with an area of 0.05. .1915 is the area that goes with a z of 0.05. I want you to go the other way around. I want the value in the table to be 0.0500. Now in table C1, that's the area in, right? That's the area between the middle. What did I say I wanted? You caught me and I didn't catch myself. I wanted the area outside, right? I wanted the area at the top. Let me draw the picture. This is what happens when I don't draw the stupid picture. Normal distribution, right? I want 90% in here. That means I want this to be 5%. And I want this to be 5%. So do I want the number that goes with 0.05? Hannah, what do I want? 0.10 would tell me from the middle, 10%. I want the upper bit. Say it louder. I want 0.45 because this, which is what I get from that table, is half of 90. Find me the closest number to 0.45. Between 1.64 and 1.65. So how about we use exactly the middle? Gee, what a familiar looking number. If I want 95% in the middle, what's this half? That would be what's out here, is 0.025. So what's inside? 0.475. And now what do you notice on that table in Appendix C1? About 0.475. Something very special about the number 0.475. It's in a box. And what Z goes with it? Again, what a familiar number. Didn't I just use 1.96? I promise I'm not pulling these numbers out of my ass. If I'm doing 99%, then this should be 0.005 up here and 0.005 down here. What should be on that side? And if I go and I look on my table, Z equals it's between 2.57 and 2.58. If I actually use the Excel command to do the inverse normal, I get that number. Now, what does this mean? This means that those numbers, 1.4645, 1.96, they didn't come out of nowhere. They came out of my idea of a margin of error. My confidence interval represents the chance that the true average is within my margin of error from my point estimate X bar. The probability that the correct average, the population average, is this much above my sample or that much below my sample is my confidence level. All right, this sounds absolutely mind-blowingly dumb. All this does is it builds the same interval you were just building, only instead of starting at the true mean, we started our sample mean. And then I can say I am this confident that the true average is in here. Those of you who do lab sciences, you've built error around a value you get. This is where the error bar comes from. Exactly the same error bar you put in a lab report. So, let's suppose for a moment I go sampling and I take samples of 9 and my measurement of those 9 is 2.4. Now, because of the manufacturing process for making these items, whatever they are, I can say I expect the standard deviation to be 0.15. So, if I wanted to be 90% confident, what is the confidence interval for the true mean? Remember, I took a sample and I said the average is 2.4. But I'm 90% confident that the average is between what and what? A 90% confidence interval is found by taking my mean, subtracting, oh, wait a minute. What's the Z that goes with 90%? 1.645 times the standard error, that's 0.15 over the square root of how many samples did we take? 9. So let's do this calculation and tell me what you get. Now, I would probably call it 2.32 because I only want to go one more decimal place than I was given for my measurement. But the more decimals you give me, I'm not going to be unhappy. And the upper limit plus 1.645.015 over the square root of 9 is 2.48225. I'm 90% sure the overall average is between these two numbers. Even though I got 2.4 on the nose, there's some room for error. If I want a higher confidence, This interval is going to get bigger or smaller? Going to get bigger because the Z value gets bigger as my confidence level goes up. Assumption number one was that I knew what the standard deviation was. What do I do when I don't know the standard deviation? We'll talk about that one on Friday, and I think you all will be interested to know that this was developed by a gentleman working for the Guinness Beer Company. So Friday we'll celebrate. After class, we'll go have Guinness. Anyhow, I will see you all on Wednesday for the exam. Please remember, you are entitled to a formula sheet. And there's our point breakdown for the question breakdown for the exam. It's going to be scanned up. That's fine. If you came in late and I don't have your homework yet, come give it to me.